So for my next example, I'll show, you remember for any curve we can define the unit tangent vector. We can show that for a closed curve, the line integral of on the closed curve C of the tangent vector to the curve is equal to 0. So for a closed curve, if you consider the circulation of the tangent vector field to the curve, this will always end up being equal to 0. So why is this? Well, we have two different ways of showing this. And I'll verify this in both ways, so you can kind of see how to do it in both ways. The first way, remember that the closed line integral of the tangent vector to a curve is the same thing as, if you remember the definition of the tangent vector to the curve, it's the derivative of the position vector with respect to arc length. So this is the same thing then as the line integral of dr which is the same thing as the line integral over C. Dr is I hat dx plus j hat dy. It's the sum of two separate line integrals, and for each of these line integrals you have the integral of 1 dx by Green's theorem is the same thing as the double integral over the region control covered by C of negative the partial derivative with respect to y of the constant function 1. And the derivative of a constant is 0, so this is going to be equal to 0. And likewise for this integral, you have the exact same thing, only it's dq dx, and q here is 1. So both of these integrals are 0. This is going to be 0, and this is going to be 0. And therefore we've shown that exactly what we want to show. This is method 1 using Green's theorem. We don't need to use Green's theorem. This would be possible to do without Green's theorem, and I just want to show a different method of showing this, just for illustrativeness and kind of showing that there are typically in mathematics multiple ways of going through and getting the solution to a given problem. Remember that any line integral be evaluated from 0 or from A to B, where B is the beginning point and Right? A is the beginning point and B is the end point. In this case, this is going to be t hat, which we know is r prime of t divided by the magnitude of r prime of t. And ds, remember, is going to be the magnitude of r prime of t, dt, when we go to evaluate this. These two magnitudes cancel one another out, leaving for us the integral from a to b of r prime of t dt, which by the fundamental theorem of calculus, in each component of this vector will be exactly r of b minus r of a. And because this is a closed curve C, r of b is equal to r of a. So this line integral is equal to 0. So this is just a nice example, just kind of showing that typically there are multiple different ways of proving something in mathematics. It all just depends on what method you want to use, but Green's theorem is a nice way of showing this. So the next thing I want to talk about in this lecture will be how to extend Green's theorem to more complicated domains. And specifically, this is domains with holes in them, so non-simply connected domains. And we know that from some of the examples that we've seen already that simply connected domains are a very, very important thing to think about. Because we've seen certain examples of vector fields defined on non-simply connected domains that are very kind of tricky to deal with. So the question how to extend Green's theorem to non-simply connected domains. And the idea here, and the way that we're going to do this, is the following. So let's take a general domain. R. And we'll just put one hole in R. So I'm going to call the curve that traverses R C, capital C, and this is traversing R in the counterclockwise direction, just like all of our other traversals before. And R is all of this space right here. And this hole I'll call, the contour around this hole I'll call C1. And I'm going to traverse this hole in the opposite direction. Right, this is important here, and you'll see why in a second. Because the trick that we're going to use is the following. It's going to be a similar trick to what we did before. I'm going to trace, and I'm going to form a cut here. We'll form a cut right here, and we'll call this cut trace. In this direction, gamma. So we cut our domain R, we cut right into that hole. And I'm going to define the following. I'll define path from here all the way around, tracing this region. To be C1 epsilon, or sorry, not C1 epsilon, we'll just call it C epsilon. And then we continue this tracing in here until we cut, and I'll call this gamma 1 epsilon, this piece. And then we have another piece going around the curve, around this in the opposite direction. We call this portion C1 epsilon. And then lastly, we have one final piece that we'll call this final piece gamma 2 epsilon. And now the trick here, and the amazing thing here that happens, is if we consider the union of C epsilon with gamma 1 epsilon, gamma 2 epsilon, and C1 epsilon, this region, all right, this is a closed curve surrounding a region R. Not R, but it's a little bit smaller than R, so surrounding a region R epsilon with no holes. Now, if you consider all of this space right here, there's no holes in this region right here that's surrounded by this blue curve. And therefore, we can apply Green's theorem to this region right here. Specifically, we can consider the line integral closed line integral over this entire curve of f dot dr, and this is going to be exactly equal to the double integral over r epsilon of the curl of f. And just like before, what we're going to do is we're going to consider the limit as epsilon goes to 0. And as epsilon goes to 0, gamma 1 epsilon becomes just the curve gamma, which is that cut that we defined initially. As does gamma 2 epsilon. But gamma 2 epsilon becomes gamma traversed in the opposite direction. Because of the fact that on the blue curve we traverse like this on gamma 1 epsilon and like this, the opposite direction on gamma 2 epsilon. The curve C epsilon becomes just the curve C because these boundary points match up as epsilon goes to 0. The curve C1 epsilon becomes C1. And lastly, the domain R epsilon just becomes the normal domain R because all of these points that are removed in this cut go away. Or they're absorbed as the curves gamma 1 and gamma 2 come together. So from an integration standpoint then, this integral becomes the same thing as the closed surface integral over C union gamma union negative gamma union C1 this is going to become the double integral over R of the curl of f dot dr or dA. So just like before, this will actually simplify a little bit. It's the closed integral over C of f dot dr plus closed integral over gamma of f dot dr minus the closed integral over gamma of f dot dr, because the integral over gamma is negative gamma is the same thing as negative times the integral over gamma, because negative gamma is just gamma traversed in the opposite direction, plus the integral over C1 of f dot dr. This entire thing is equal to the double integral of the curl of the vector field f dotted with dA. And actually I should say, well, dA you can think of as a vector quantity if you want. It's k dA, but this is dotted with k hat dA. And it's the same thing down here. This is how I typically like writing it. So just like before, these two integrals are the same thing. And what's interesting here is that we have this integral does not vanish. This is saying that the circulation around any curve C of f dot dr plus the closed circle contour integral around C1 of f dot dr. So this sum is equal to the double integral of the curl of f over the region R. So this is the correct form for Green's theorem in the plane when you have a region with holes. So you have a region that's not simply connected. And this actually explains a number of different things. Specifically, in a second, we'll use it to explain the example that popped up a couple lectures ago. So specifically, another nice way of writing this would be that for any boundary contour C, if your region has one hole in it, then the line integral, the circulation around the vector field F around that C is going to be the double integral of the curl in your region minus the integral of f dot dr over C1, where C1 is a closed contour that surrounds that, or the boundary that surrounds that hole. And C1 is traversed in the opposite direction, so it's the clockwise direction, whereas C is traversed in the counterclockwise direction. So this is Green's theorem. So R has one hole. And as you might readily consider, what if it has multiple holes? So it's topologically possibly very complex. You'll get a very similar formula if it has n. You just need to do this process, this cutting process, for each new hole, for each new individual point that's removed from the region R. So the formula that you end up getting is going to be very, very similar to the one we just got, only you're going to have a summation of different line integrals that you have to evaluate here. Specifically, you'll have to subtract out around each individual missing portion of the domain. You'll have a contour CI, which is traversed in the clockwise direction, and you have to sum over each one of them for I from 1 to n. And this is going to be the flux, or this circulation around the larger contour. So the main boundary contour C looks like this, and then for your region here, you'll have C1, say, C2, C3, and so on and so forth. So you'll have to compute an integral around each one of these subcontours and subtract it from the double integral of the curl in the region R to the general Green's theorem. I'm not going to go through and prove this. The proof is almost exactly the same as the proof of this one whole theorem, and you can actually see it in the book as well. But so let's apply this to that example problem, and I'm not going to go through and recalculate things, but if you remember, for the vector field F from R2 minus the origin to R2, this is the vector field F is equal to x over, or negative y over x squared plus y squared and x over x squared plus y squared we computed that for a circle of radius epsilon, over a small circle of radius epsilon, of the line integral is equal to 2 pi. So this is a circle of radius epsilon. The line integral over c epsilon, and this is in the counterclockwise direction, was 2 pi. So if we reverse the orientation, so we say c epsilon is the circle in this direction right here. So in the clockwise direction, contour integral over c epsilon of f dot dr is going to be equal to negative 2 pi. And now if we consider any other curve that we want surrounding the origin, call this a curve C. This more advanced version of Green's theorem, by the way, remember that we found that the curl of this vector field on its domain here is equal to 0. So for any other curve C, from our second form of Green's theorem, the flux, or the circulation around the curve C of f dot dr is going to be equal to the double integral over r of the curl of f dr minus the integral of c epsilon of f dot dr. This is from the version of Green's theorem that we just proved for a domain with holes in it. Well, the curl of this vector field on the region R itself is 0 everywhere. So this is going to be 0, entire integral. And the line integral of f dot dr computed in the reverse direction, so in this direction right here, is going to be negative 2 pi. So the closed contour integral over C along any curve by Green's theorem is going to be equal to the constant 2 pi. Or the circulation of this vector field around any curve, no matter how complicated it is, will be 2 pi. And you can take the limit here. Epsilon here is arbitrary, so you can go as small as you want for epsilon. And this is just exaggerated in this picture right here. But this is explaining for us where that 2 pi is coming from, and why, in general, for a vector field that is curl free or irrotational, it's not always conservative, because directly because of this result, this extension of Green's theorem. So the idea of topology is very important when we're discussing theorems in regards to vector fields. The last thing that I want to point out is that there are actually two equivalent formulations of Green's theorem in the plane. The formulation we've related to curl, but it turns out we can also relate this to divergence. So we have what's called the curl form and the divergence form of Green's theorem in the plane. And sometimes this is useful, actually, even in just like applications, specifically considering like the flux out of a given region in two-dimensional space, in 2D space. But we're going to see that there's an even bigger application and reason that we're going to kind of point this out right now, because it's very useful when we go to extend Green's theorem in the plane to three-dimensional space, to 3D. So let's assume we have a region R with no holes in it. Could have holes in it. We know that we can define the unit tangent vector to the boundary curve R. We can also define the unit normal vector to t hat, as we've talked about. And for a 2D curve, defining n hat is actually very, very straightforward. You can get it very, very nicely directly from t, actually. You know that t hat is equal to dr ds, or the derivative of position along the curve with respect to arc length, which is dx ds dy ds. We know that the normal vector to this curve is going to be at a 90-degree angle to t hat at every single point. So you can ask yourself, what is the vector that is always going to be at a 90-degree angle to this t hat? What I'll do is actually simplify it. I'll use subscript notation for the derivative here, just to simplify our expression here. Well, we could think about that for a second, but if we define the vector n hat, it's going to be a 90-degree angle to t hat, so it has to be perpendicular and point outwards. N hat is going to be exactly equal to the vector ys negative xs. Remember, our orientation here is a counterclockwise orientation. So the vector ys negative xs will be a 90-degree angle, and it will be point perpendicular to t hat in the direction of the outward normal. You can go through and show that they're perpendicular directly by taking the dot product. It's going to be xs times ys minus xs times ys, which is equal to 0. So what we'll also do is we'll define the vector field. So we have the vector field F already, which is the vector field PQ. I'm going to also define the vector field G, which is the vector field Q negative P. And it should be clear to you that if we take the dot product of F with T, this is the exact same thing as the dot product of G with N. It's just equal to P times XS plus Q times YS. And in what we're about to do, it's important to also note that curl of the vector field F dotted with K hat, which is equal to dq dx minus dp dy, is the same thing as the divergence of G. You should check all of these. I want you to go through and just check to make sure that all of these things that I've written down check out and are correct. But I guarantee they are definitely correct. You can see that directly. It'll just be x derivative of G is dq dx plus the y derivative of G, which is negative dp dy. Right, so this is exactly a direct kind of check right there that I just did. So we keep all of this in mind and remember that the Green's theorem in the plane, in terms of its vector notation, we've been writing it as the contour integral of over C of F dot T hat ds, or F dot dr, and this is the same thing as the double integral over the region R of the curl of the vector field F dotted with K hat dA. This is the curl form of Green's theorem. Using these nice things we've shown right here, we can also write an equivalent form to this first form as the contour integral of G dot N ds, the closed contour integral of G dot N, is equal to the double integral over R of the divergence of G dA. This is sometimes called the divergent form. of Green's theorem. And this is special because the idea here is that this divergence form of Green's theorem is actually giving us something very, 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 very nice. Because remember, P and Q are completely arbitrary functions. So the idea is that if this is true for Q and P, which are arbitrary functions, this can be true for any vector field G. And the point is that, right, fundamentally these two things are expressing the same relationship, but they're expressing it in different ways. The curl form of Green's theorem is saying that the total circulation around any closed curve of a vector field F is exactly equal to the accumulation of curl inside the region R. The divergence form of Green's theorem is saying that the total flux of the vector field normal to the curve C, the stretching of the vector field normal to the curve C, is exactly equal to the accumulation of divergence inside the region R. So the accumulation of stretching of the vector field inside the region R. So that both of these forms are equivalent in the plane. You can use either form in. They're essentially telling you the same thing in the plane. If you use the fact that F is equal to or related to G through this relationship. But we're going to see that there's a very, very nice expression here. In 3D when we go to extend Green's theorem. So these two forms, I'll write this down. Are equivalent in the plane. However, each has its own unique extension to 3D. And this is what we'll be moving into in the next few lectures. Right? The extension of Green's theorem into 3 dimensions. The first form is called in 3D Stokes theorem. And in 3D, the second form is called the Divergence theorem, or Gauss's theorem. And they're both very, very special, very, very much more general things or theorems that help us very, very, very much when simplifying and when going through and computing integrals. So I'll end with one final example, and this example is going to show the power of the divergence form. And both of these forms, the curl form and the divergence form, are very, very helpful in terms of getting simplifications. So the one of the big collection of simplifications for vector fields that are very useful are called the Green's Identities. And we're just going to go through right now, and I'll prove the first Green's identity, which is a super useful formula relating that we can directly prove using Green's theorem. This is saying that for a region R, the divergence of a function f times the gradient of some function g the double integral of this over region R is going to be exactly equal to the closed contour integral over its boundary of f, which is the function f, times partial g partial n ds. So the accumulation of this integral right here, where dg dn is just the normal derivative of the function g, or I should say the directional derivative in the normal direction of the function g. So to prove this, we're going to apply Green's first identity. Sorry, not Green's first identity. We're going to prove Green's first identity. We're going to apply Green's theorem in divergence form. With g equal to the function f times the gradient of g. In which case, this integral that we start with, this double integral, just becomes equal to the closed contour integral over C of the vector field G, because this is the vector field capital G, and by the divergent form of Green's theorem, the double integral of the divergence of G will be equal to the dot product of G with n hat. This is going to be G, which is f times the gradient of G dot product with n hat ds. That's the contour integral of this, which is the same thing as the closed contour integral of f times the gradient of G dotted with n hat, which is exactly equal to the closed contour integral over C of f times partial g partial n, because this is the definition of the directional derivative in the direction n. And this concludes the proof of Green's first identity. So what you might be interested in doing, and what I recommend doing, is going through and checking Green's other identities for yourself. It'd be a very good, useful kind of practice tool to go through and do. So look at the second identities and the third identities and see if you can go through and use Green's theorem to prove these identities. But thank you very much for coming to lecture today. I hope you learned something and had a great day.